In the last class, I introduced this notion of a kernel. So a kernel is just a symmetric map, right, from X to R. So it takes two symbols from the domain as input and output some real number. So that's a very generic definition. But then what we're interested in are kernels which look like inner products. So in addition to it being symmetric, we also want to make sure that if you take any n points and you form this particular gram matrix, then this gram matrix should be symmetric and positive semi-definite. All right, and such a kernel for which you take any n points from the domain for every n, the kernel or gram matrix is positive semi-definite. That's what we call a positive definite symmetric kernel. All right, and clearly if K corresponds to an inner product in over some high dimensional space, then the kernel is guaranteed to be positive definite symmetric. But there's also another result which I'll state a little more formally later, which says that if you have a positive definite symmetric kernel, then that corresponds to then there exists a mapping from X to a higher dimensional space, such that the inner product is equal to the kernel, is equal to the kernel evaluation on that pair of points. Okay. So, and we saw that the advantage of using a kernel, where this kernel corresponds to an embedding into a higher dimensional Hilbert space, is that now techniques such as support vector machines can also be extended to kernel support vector machines. So when you're designing classifiers, instead of just, so for SVMs, we developed a nice framework where we had an efficient algorithm in the realizable case that actually corresponded to empirical risk minimization. In the unrealizable case, it did not, but still it performed reasonably well. And there were also theoretical bounds that we could derive based on the margin. So all of these tools and techniques also extend to kernel support vector machines. So just by applying this kernel with perhaps just a little bit of additional computational complexity, we now have a much broader class of classifiers. Right? We don't have to just restrict ourselves to linear classifiers. We can also we have a rich class of non-linear classifiers for which we have an efficient algorithm and some theoretical margin-based bounds. Okay, and that guarantee was essentially given by this representer theorem, which said that if you have an embedding into some dimensional space, some Hilbert space, then the solution of any optimization problem that look like this, in particular the support vector machine optimization problem, has a solution which can be expressed as a linear combination of the embeddings of the data points. So in other words, to solve the optimization problem, to solve any optimization problem that looks like this, it's enough to optimize over just these coefficients alpha 1 through alpha n. All right, which is and now the complexity, instead of scaling in the with the dimension of the feature space, now the complexity just depends on the number of data points involved. All right, so all of this is okay, assuming that you have an embedding into, someone gives you an embedding to a higher dimensional space and therefore explicitly specifies the kernel. Right? If someone tells you that this is a positive definite symmetric kernel, then you can go ahead and use all of these techniques, even without knowing what the exact embedding is. But how do we decide whether a particular map is a kernel map, is a positive definite symmetric kernel map or not? All right. So we saw a couple of examples. So firstly, the polynomial kernel, which is a positive definite symmetric kernel because it corresponds to an inner product, and you can give an explicit form for the embedding. All right. So the polynomial kernel corresponds to an inner product over a feature space that is d plus 1 to the k dimensional. All right. So we'll look at some more examples of kernels and see a general technique to prove that whether a particular kernel is PDS or not. All right, so let's see some kernels that are commonly used in the literature. The second kernel is the Gaussian kernel. And this has a parameter, so k of x prime is just e to the power minus norm of x minus x prime square divided by 2 sigma square. So this is a free parameter sigma square, and you can vary the parameter. You can think of it as a hyperparameter when you want to implement your classifier. All right. And even though this doesn't look like an inner product, this happens to be a positive definite symmetric kernel. And the intuition is that if x and x prime are sufficiently close to each other, then their inner product is large. And if they are sufficiently far apart, then their inner product is small. So the geometry is now different. It's not the conventional cosine based inner product that we're talking about. This is some other kind of an inner product over some higher dimensional space. In fact, it turns out to be an infinite dimensional space. The other commonly used kernel is a sigmoid kernel. So k of x prime is tan h of a times the inner product between x and x prime plus b. For some a greater than 0 and b greater than or equal to 0.
Positive definite is actually defined for matrices.
Correct.
Like my understanding is that all the eigenvalues have to be positive, and there
Yes.
things like x things matrix into x transpose into
Correct. Yep.
But that is not matrix thing.
It's not a matrix. That's why it's a definition. It's called a positive definite symmetric kernel, and that's because if you take the Gram matrix, then it should be positive semi-definite.
Which matrix?
The Gram matrix. So if you remember that a kernel is defined to be PDS, positive definite symmetric, why did I have that? If for every set of n points, right, you form this Gram matrix, which is k of x1 comma x1, k of x1 comma x2 up to k of x1 comma xn, and all the way for all possible pairs. This matrix is symmetric and positive semi-definite.
So we're talking about this matrix when we implicitly.
Correct. Implicitly, we are assuming that this matrix is guaranteed to be positive semi-definite. All right. That's why positive definite symmetric. Okay, so this kernel, the sigmoid kernel, also happens to be a positive definite symmetric kernel. Here is an example of something which is not a positive definite symmetric kernel. K of x comma x prime equal to indicator norm of x minus x prime less than or equal to 1. All right, so show that this is not a PDS kernel. So when you want to show that this is not a PDS kernel, it's relatively easy because you just need to find, let's say, 2 or 3 points or 4 points or whatever, and just one example for which the Gram matrix is not positive semi-definite. All right, in this case, I think you can pick some 2 points and show that for those 2 points, the Gram matrix is not PSD. So the examples that we've seen so far are all mappings from RD to some Hilbert space. So in RD, there's already an underlying inner product. But there are also examples where the underlying domain is not a vector space at all. All right. So one such example is the following: the sequence mismatch kernel. So X is the set of all sequences on some particular alphabet. Let's say finite. For example, it could be set of all binary strings, all right, and k of x comma x prime. Now x and x prime are substrings of potentially different length. This is equal to the number of common subsequences of the pair x comma x prime. All right. So, for example, if you have 0, 1, 1, 0, 1, 1, and 0, 1, 1, 1, 1. All right. So, in this case, 1, 1, 1, 1 is a common subsequence. 1, 1, 1, because you have 1, 1, 1, 1. Right? 0, 1, 1, 1, 1 is also a common subsequence. 1, 1 is also a common subsequence. 0, 1, 0 is not a common subsequence. Okay. So one can show that this also is a positive definite symmetric kernel. Okay. And this is particularly useful when you're talking about strings. Let's say you want to do some classification over text. All right, then you need an embedding into some Hilbert space, and this gives you a natural embedding. So let's say you want to design an SVM classifier for text, then this is one choice of a kernel that you can use. This also happens to be a PDS kernel. So in many cases, proving that something is not a PDS kernel is relatively easy. You just need to give a counter example. But to prove that something is PDS is not easy. You can't construct examples to show that it is PDS. All right. So here are some general techniques just by looking at some properties. Right. So firstly, if F, let's say, is an arbitrary map from X to R, then this is a PDS kernel. Why is this a PDS kernel? Why is this a PDS kernel? Again, let's take any endpoints. X1 through xn.
Yes, everything comes and have to be more term. In the sense,
No, no,
vector x moves away from the origin.
nothing.
F of x should also increase.
No.
There is no such.
No. Let's construct the gram matrix, which is x1, f of x1, f of xn. x1 I'm sorry? It's a, and what is it equal to?
X1, x2.
Correct. So it's just f of xn times right. So this is positive semi-definite for every x1 through xn. The second is that if you have two kernels, if K1 and K2 are PDS kernels, then, so firstly, K1 plus K2 is PDS. Why is that the case? Sum of two positive semi-definite matrices should also be positive semi-definite. Right. So basically, kernels inherit all the properties, general properties that PSD matrices have, right? Because G1 plus G2 is PSD if G1 and G2 are PSD. Because X transpose G1 plus G2 times X would be equal to X G1 X transpose G1 X plus X transpose G2 X. Both of them are guaranteed to be greater than or equal to 0 because G1 and G2 are PSD. Therefore, G1 plus G2 should also be PSD.
The above equation, top of the page.
Yes.
How did we just say it was PSD by infinite equation?
Which one?
The top one.
This one.
Yeah.
That's because you can. You.
And then how do we?
Oh, okay. So then this is some vector, right? So let's call this vector F. So this is of the form FF transpose. Now you take any X transpose FF transpose X. What is this equal to? This is X transpose F times F transpose X, which is just X transpose F the whole square, right? Which is guaranteed to be greater than or equal to 0. Okay, so K1 plus K2 is guaranteed to be PDS. Similarly, alpha K1 plus beta K2 is PDS, but not for all alpha and beta. You want, what would you require? Yeah? Positive. Again, all of this is inherited from the properties of PSD matrices. Second, so in fact, they just have to be greater than or equal to 0. Guaranteed that it's still PDS. Right. So The third is that k1 times k2. So basically k k1 of x1 x2 times k2 of x1 x2 is also PDS. Show that this is the case. The hint is that if you take the gram matrices, then the gram matrix corresponding to K is the element-wise product of the gram matrices corresponding to K1 and K2. Okay. The other property is that if K1, K2, and so on, so if you have a sequence of PDS kernels, infinite sequence of PDS with a limit. So basically note that each k1, k2 and so on, these are functions, right? So if the sequence of functions has a limit, let's say in L2 or whatever, then Kn is PDS. And again, this follows from the property that if you have a sequence of PSD matrices which converges, then this will also converge to a PSD matrix. The fourth property, which I'll just state, is that again if K is a PDS kernel, then K prime of x1, x2, which is the normalized version of K, this is also PDS. So these are some basic properties of PDS kernels which allow us to either construct new kernels or prove that certain kernels are PDS. Right? So if you start with, so first property is that the product of, if in any kernel that can be expressed as f of x times f of x prime is PDS. And if you have two PDS kernels, then any linear combination, any positive linear combination is PDS. Element-wise products of PDS, or the product of PDS kernels is PDS. Normalization of a PDS kernel gives you a PDS kernel. And if you have a sequence of PDS kernels, then the limit is also going to be a PDS kernel. Okay. So let's try to investigate at least some of the kernels that we've seen so far. The first that we saw was a polynomial kernel, right? C plus x1, x2, inner product between x1, x2 whole to the power k, right? So let's go back to example 1. for some C positive. What properties, how do you prove that this is a PDS kernel? Without explicitly going through the embedding, trying to find an embedding.
Can I factor it? It's like can I factor it as two things like k by 2 k by 2 powers and less than or equal to
Not
that.
even that. So what's the, okay, let's break it down into individual components, right?
So
Inner product between x1 and x2, is that PDS?
yes.
It is, right? It's an inner product.
So the product can be extended to any finite number of products which is needed.
Exactly. So basically, this property 2.3 that we had, this also extends to any product of any finite number of PDS kernels, right? And that's all there is. So first, so this is a PDS kernel, right? K2 of x1, x2 equal to a constant. This is also a PDS kernel, because if you take the gram matrix, it's just C times the all ones matrix, which is PSD. So the sum of K1 and K2 is PDS. And K1 plus K2 whole to the power K is PDS. Now let's take the Gaussian kernel. K x1 x2 is e to the power minus x1 minus x2 square by 2 sigma square. How would you approach this? So just to help, let's simplify it a little bit. I'll write this as e to the power minus norm x1 square by 2 sigma square times e to the power minus norm x2 square by 2 sigma square times e to the power minus inner product between x1 x2 by sigma square. Okay, I'm sorry.
See, graph matrix is always all the elements are positive. Then isn't it always created?
No? Just because the entries are non-negative doesn't mean that the matrix is PSD. For example, 0, 1, 1, 0, the matrix. Okay, so fine. So this is what I have. So I can express k of x1 comma x2, the Gaussian kernel, in this particular form. All right. Let's break it down into three things. So first, it's a product of three functions. Is the first function a PDS kernel? Or let's just take the product of these two functions. Is this a PDS kernel? Say k1 of x1 x2 equal to e to the power minus norm x1 square by 2 sigma square times e to the power minus norm x2 square divided by 2 sigma square. All right. Why is this PDS? Correct. So it's from the first property that it's equal to f of x1 into f of x2 for the same f. Okay. So now if I'm able to, if I can show that this is a PDS kernel, then it means that the product of these two should also be a PDS kernel, and therefore the Gaussian kernel must be a PDS kernel. So let me define k2 of x1 x2 to be e to the power inner product between x1 and x2 divided by sigma square. Okay. Correct. So basically what I'm going to do is try to express this as a limit. Let's take the Taylor series expansion of e to the power t. What is it? So it's summation, say t equal to or I equal to 0 to infinity. Yeah. So x power I, t to the power I by I factorial, or in this case, inner product between x1 and x2 by sigma square whole to the power of I times 1 by I factorial. All right. Is this PDS? Why? Right. So firstly, this is PDS, and therefore this is PDS. Anything raised to the power I is PDS. Any scalar multiple is by a positive constant is also PDS. So each of these PDS for every I, and this converges to a well-defined limit. Therefore, this is PDS. Right? And since K1 and K2 are both PDS, is also PDS. So that's one approach to show that the Gaussian kernel is a PDS kernel. The other way is to try to explicitly construct the embedding. All right. So I'll give you the embedding for R. All right. So let equal to r, and define psi of x. So psi of x is going to be an infinite dimensional vector whose nth component is equal to e to the power minus x square by 2 times x to the power n divided by square root of n factorial. Okay. So what would be the inner product between psi of x1 and psi of x2? This would be summation, and this is n going from 0, 1, 2, and so on, all the way up to infinity. So this is summation n equal to 0 up to infinity e to the power minus x1 square by 2. I mean, here I'm assuming that sigma square is equal to 1 times e to the power minus x2 square by 2 times x1 x2 to the power n divided by n factorial, which is exactly e to the power minus x1 minus x2 the whole square by 2. Sorry? Alright, so this is so now we also have the explicit embedding into the feature space. So the feature space is for the Gaussian kernel is an infinite dimensional space. You can use these techniques to prove that many commonly seen kernels are all PDS. So a common trick is to somehow try to expand. If you have a complicated function, let's say something like the sigmoid kernel, you take the Taylor series expansion and try to prove that each of the terms in the expansion is a PDS kernel. That should be easier to do, and so on. So these are general approaches. Yeah, but of course you have to be a little careful. Make sure that when you take the Taylor series expansion, it should be, all of the coefficients should be positive. Otherwise you can't use this particular approach. Okay, so here's another property of PDS kernels. So PDS kernels give rise to a Cauchy-Schwarz inequality. Then for every pair x comma x prime, k of x prime square is less than or equal to k x comma x times k x prime comma x prime. Right. And this is just a two-line proof. How do you prove this? It also gives a very two-line proof of the Cauchy-Schwarz inequality. The standard Cauchy-Schwarz inequality, I mean. So you take the Gram matrix for x comma x prime. This is k of x, k of x prime, k of x prime x, which is equal to k of x prime. K of x prime. This is guaranteed to be PSD. Therefore, the determinant should be greater than or equal to 0. But what is the determinant of G equal to? K of x prime minus k x prime the whole square is greater than or equal to 0, which is exactly what we wanted. All right, so again, this also gives a proof of the standard Cauchy-Schwarz inequality. Just by observing that the inner, if you take this Gram matrix for the standard inner product, then that is also positive semi-definite. Any questions? So as we discussed earlier, if you take any PDS kernel, then that gives rise to an embedding into a Hilbert space, the feature space as we call it. But for a Hilbert, as it turns out, there's a specific class of Hilbert spaces for which there exists a kernel. Right? So we've defined one thing. So if there is a kernel, which is PDS, then there exists a high dimensional feature space, which is going to be a Hilbert space. And there in which the kernel evaluation corresponds to the inner product between the embeddings. Right? So similarly, if I give you an arbitrary Hilbert space, then when does that give rise to a kernel, so to speak? Okay. So these are problems that were studied in functional analysis way back in the 50s, and that's where all of this theory of kernels and kernel methods came from. The roots are there in analysis. All right. So it was much later on that the machine learning community discovered this and used it in the context of support vector machines and many other problems that we'll see later. All right. So this is a class of Hilbert spaces that have been studied a lot in the literature, and these are called reproducing kernel Hilbert spaces. Right. So what is a reproducing kernel Hilbert space? So it's a subclass of Hilbert spaces, and the class of Hilbert spaces that we'll see are collections of functions from some domain to R. All right. So a Hilbert space of functions from X to R. So each vector in the Hilbert space is a function from X to R. Is said to be an RKHS if there exists some mapping from X cross X to R such that this gives rise to the so-called reproducing property. You take any f in the Hilbert space. Functions from x to r. Let's denote this Hilbert space H. For all f that belongs to the Hilbert space, f of x is equal to there exists a k from x to r. So this let me call this k x complex to r, such that f of x is the inner product between f and so k is a function that takes two inputs. If I fix the first input, then this quantity is basically a function from x r, and this is some function that belongs to the Hilbert space itself. So f of x can be obtained by an inner product between the vector f and this function kx. So in other words, for every x, there is some function kx such that for all f in the Hilbert space, f of x can be obtained by taking the inner product between f and kx. So this k is called the kernel of the RKHS. And this property that the evaluation of f corresponds to an inner product in this feature space is called the reproducing property. The reason why this reproducing property is useful to us as machine learning practitioners is that f of x could potentially be a nonlinear function applied on x. But then this, in some high dimensional feature space, within this RKHS, the evaluation of f on x corresponds to taking an inner product, which is a linear transformation on f, and this linear transformation is defined by kx. Right? Because this is, you can view this as a linear transformation of f. Sorry? Okay, great. So firstly, hopefully there's no doubt that this is a linear transformation of f in this Hilbert space, okay, which need not be a finite dimensional space. Okay, and what is the linear transformation that I am considering? It is inner product with kx. Okay, now if I want to evaluate f on x, which is essentially over the space x, transforming x to f of x could potentially be a nonlinear operation. Right? This is nonlinear operation when viewed, if you think about what happens to x. The transformation from x to f of x is nonlinear. All right? But the transformation from, say, kx to f of x is linear, because it just corresponds to an inner product, which is a linear transformation.
Just mapping to neural networks. So now a sigmoid neuron.
Okay?
So basically a mapping as a nonlinear function.
Correct.
And also can be represented as a linear combination.
So if you take a single layer neural network, then that essentially it would correspond to some nonlinear. So it could be represented as a linear transformation, but over the feature space, over a much higher dimensional feature space, potentially an infinite dimensional feature space. All right. Now, in terms of application, right, whether this can actually be used in practice is a different story. Right. In some cases, it can be. For example, this was exactly what helped us to design an efficient learning algorithm, because now all my optimization algorithms for linear classifiers could now be extended to kernel classifiers. Right. And this particular property is the underlying principle that helps us in that case is exactly this reproducing property. Right. So the fact that if you take f of x, which could be the classifier when applied to x, this can be represented as this can be thought of as a linear classifier in the feature space, because you're just taking an inner product. Is that okay?
But inner product of function f.
Correct.
I understand if there are values there. K of x is a value and we have values, but I don't understand using function itself.
So I mean, one way to think of f is, let's go back to the, let's say, right? Let's take e to the power minus, so the kernel function, right? So k of x x prime, let's say this is equal to summation I equal to 0 to infinity e to the power minus x square by 2 yeah. So maybe let me try to take the perspective of psi. So k of x prime is the Gaussian kernel e to the power minus x prime square by 2, and for this psi of x was an infinite dimensional vector, which was e to the power minus x square by 2 x to the power n divided by root n factorial. Right? So your feature space was an infinite dimensional space. Okay. So one way to think about it is, suppose I have some function f. right? Which maybe can be represented as a Taylor series. Okay, so express in f in the Taylor series approximation. So fn, the nth component of this f, right? So f is a function, and this has an equivalent representation in the higher dimensional space, which is whatever the nth let's say that I have f of x, which can be represented as I equal to 0 to infinity f of whatever fn x to the power f. Okay. Suppose that this were the case. Then, so fn does not, maybe let me write this as alpha n. F of x is summation I equal to 0 to infinity alpha n x to the power n. And this is, let's say that this is something that converges for every x. So it has a well-defined Taylor series expansion, and maybe it requires some additional properties, as we'll see a little later. So now let's take the representation. So I'll represent f as an infinite dimensional vector, f1, f2, f3, f0, f1, f2, f3, and so on. And this will be basically alpha n root n factorial times e to the power x square by 2. Let's say this is the embedding. So this is the so the function f corresponds to this vector f1 through fn. So f1, f0, f1, f2, and so on. This vector belongs to this RKHS, which is defined by the Gaussian kernel. You need certain additional conditions maybe for on alpha 1 through alpha n for a particular f to belong to this Hilbert space, but let's not worry about that for now. So this is the vector representation of the function f. The nth component of the vector is alpha n, where alpha n is the nth term in the nth coefficient of the Taylor series expansion, square root n factorial e to the power minus x square by 2. Okay. I am sorry? Which one? No, this is how I am defining fn, the nth component of the vector representation of f, the representation in the Hilbert space. It depends on it depends on x, yes. Which one? So remember that f is a representation. Which one? F of x? Correct. Okay, so this is maybe not a very good example. I see. So yeah, I need a representation that does not depend on x.
I think f would just be the alpha and in factorial part would be the kx.
Let me see. Well, basically what I want is that e to the power x minus x square, e to the power minus x square by 2, x to the power n. Okay, let's see what happens. So let me take the inner product between f and kx okay, let's see, the corresponding inner product here is summation to infinity alpha n kx okay.
If it's not dependent on x, it should not be dependent on
F should not depend on x. So let me put this in a slightly different way. So let's look at, I'll view the Hilbert space a little differently. So this is kx prime. Let's take any f from x to r. In this case, f from r to r. R to r. Basically, what I want is, so this is a function from r to r, kx, and the Hilbert space is a collection of functions from r to r. Okay, let's suppose that the inner product is integral from minus infinity to infinity g1 g2 g1 of t g2 of t dt. Suppose that this is the inner product that I've defined. Then what I want to say is that f of x can be written as integral minus infinity to plus infinity sum f prime of t e to the power minus x minus t the whole square by 2 dt, where this f prime is the representation of f in the reproducing kernel Hilbert space. So in general, it may or may not be easy to find this particular representation. And most Hilbert spaces of functions happen to be reproducing kernel Hilbert spaces. So the class of RKHS is turns out to be very, very rich. It's harder to find an example which is not an RKHS. All right. Questions? Okay, so another fact is for in RKHS, the kernel is unique. So every RKHS has a unique kernel. So now, I mean, we've seen some properties of kernels and examples of kernels. Let's see how we can use kernels to design classifiers and other kind of, and how kernels can be used in various other problems as well. All right, so firstly, we've seen that for kernel SVM, we've seen that in principle you can solve kernel SVM by solving another linear program, just as we had for standard vanilla SVM. But similarly, we can also extend the SGD for soft SVM to SGD for kernel soft SVM. So you're given a bunch of data points x1 through xn, and the SGD, kernel SGD would work as follows. So you initialize some vector theta naught. Let's say you set it equal to 0. Remember that all of these are in Rn, where n is the number of data points that you have. So for t time steps, you do the following. You set at to be equal to 1 by lambda t theta t, and then every step you choose I uniformly at random from 1, 2, 3 up to n. You pick a random data point, and you do the following. So theta t plus 1, the ith or the jth component of theta t plus 1, this is equal to, okay, let's do this is, you set it to be equal to theta t of j. You don't change it for j not equal to I. Whereas the ith component, you modify it depending on what is x comma y. So this is equal to theta t of I if yi times summation j equal to 1 to n aj or at j k xj xi is greater than or equal to 1, and it's equal to theta ti plus yi else. So basically, if you're classifying correctly with a suitable margin for the ith data point, then you don't do anything, you don't make any change to the coefficients. If you don't have sufficient margin, then you set theta, you perturb it a little, and the amount you perturb it is exactly equal to yi. All right, and the output you basically output the vector a, let's say a tilde, which is 1 over t summation t equal to 1 to t et. This essentially mimics everything that we did in soft SVM, except that instead of using the inner product, we are using k of xi xj. That's it. And at the end, instead of outputting the exact coefficients, the output is not a d-dimensional vector, but instead it's an n-dimensional vector. All right. So the classifier would be is indicator summation over I equal to 1 to n a tilde of I times k xix greater than 0. Any questions?
What are we iterating through? I use iteration step.
Sorry.
Training step.
No. So T is the training step. Right. So T is the Tth training step. You are picking an I uniformly in each training step. You are picking one of the data points, the ith data point, uniformly at random. All right.
Like how we did it for just SGD.
Correct.
If you have to do it for SGD with no any other update,
Then you may need to change things suitably. So this is very specific to. So one thing to note is that if you use vanilla SGD, then you don't need to keep track. So remember here we are not. So theta t is not the xt, or it's not wt, the one that we are interested in. All right. The quantity that we're interested in is this, right? So in other words, theta t essentially represents the aggregate of all of the gradients that we have seen up to the tth step. If you recall how we derived this, for the specific objective function that we had, vanilla SGD reduced to this particular algorithm. All right. If not, then again you would need to evaluate the gradient suitably. So it would look a little bit different. That's all. But in the end, you still have whether it's SGD with momentum or let's say with a proximal term or anything else, it would still just require you essentially replace the inner product with k of xi xj. But the important thing is that you're always updating the vector a, which is an n-dimensional vector, and not any other particular coefficients. Does that make sense?
Is 80 like update?
I'm sorry?
Is 80 means update?
So 80 is basically what we're interested in are these coefficients, right? And 80 is the whatever, it's like an estimate of A after the tth step.
Because it was reducing the magnitude, so it should be
It was reducing?
the magnitude as time step processes.
Correct, but that's because theta t is growing in magnitude proportional to t in some sense, right? Because theta t at every step we're just adding something or keeping it the same. So potentially that can keep blowing up as t tends to infinity, but this normalizing factor ensures that that does not happen. Any other questions? Okay, so maybe this is a good point to stop here. In the next class, we'll see regression, linear regression and kernel regression. And we'll also see a little bit about PCA. That's the plan for, let's say, the next class or so. So that will mostly cover what I want to say about kernel methods. And then we'll switch back to more general topics. There are certain topics that I want to cover. One is a little bit about regularization. I want to say something about boosting, which is so one way of designing a learning algorithm that we saw was empirical risk minimization. And everything that we've seen so far is some variant of empirical risk minimization. But there's another approach which is used also very frequently in practice, where you don't do empirical risk minimization, but instead you try to train or design a learner which doesn't perform great. So it doesn't achieve a generalization error that vanishes. But instead it does, what it achieves is better than just a random guess. And then you try to improve that through a process called boosting to design a better learner. And it turns out in practice, some of these approaches can work very, very well. All right. In fact, that gave rise to a whole other theory of what is called gradient boosting. And we'll maybe see that if time permits. Okay. So let's stop here.